Hi everyone. So today we get into a second way to solve differential equations. The first way was separation of variables, and now we're going to look at a second method, which is also very useful, both simple and a lot of differential equations which can be solved this way. So let's look at an example. Suppose we have dy dx, I could have written y prime as well, is equal to x plus y. Okay, so first thing to notice is I'm using x as the independent variable rather than t. Both of those are used kind of on and off, and I'll just for a little variety, we'll use x instead. So anyway, there it is, and notice that this thing cannot be separated so that y's are all on one side and x is on the other, right? You try to do it algebraically, moving it over and such, and it doesn't work. So that's not an option anymore. Notice it's a first order. It's also linear because the things you're doing with y and the derivative of y, you don't have any square there. You don't have a square root. You don't have 1 over that. You don't have the sign of it. You can do anything you want with the x that you want. It's still linear, but these things have to stay just basically the way they are. You can multiply them by x's, but you can't change the form of these things, as we've talked about. So anyway, how do we do it? Well, in this chapter, we are going to find 3 ways to solve that thing. And we're going to hit the first one today, which is basically doing it analytically, which means you do it by solving equations and such rather than using graphs or using numerical methods or something like that. Okay, those are the other 2 ways we're going to do it. In fact, years ago when I first started teaching calculus, there was kind of a whole new approach to teaching calculus, which emphasized the fact that whenever you do a math problem, you should think of it and try to solve it different ways. One way is analytically, which means you basically try to find the solution. You go through the algebra, the calculus, everything you need, like we've been doing, and you solve it that way. Another way to do it is graphically, which is what we've already been doing, right? When we did the phase diagrams, and we said, oh, okay, what were some of them we did? We said if this is y and this is dy dt, and that graph looks like that, then we just looked at it and we said, oh, that means if you start right here, the solution's got to look something like this, right? That's what we did in a previous section. So that's graphically, right? We're not getting an analytical solution, but we're doing it graphically. And then the third way is numerically, where basically you look at the numbers and kind of like when you have a graph. If you have a graph and you want to know what y equals x squared looks like and you have no idea, the best way to start is just by putting in numbers, right? You put in various values for x, you evaluate what those are, and then you plot them, and you get the graph. So that's kind of a numerical way of doing it. So anyway, we're gonna hit so those are 3 different ways of solving problems and thinking about problems. And ideally, you should try to solve every problem all those various ways, because you get a deeper understanding of the problem by solving it various ways. The philosopher Immanuel Kant, probably the greatest philosopher who ever lived, maybe outside of Plato, said that he said, I don't really feel like I understand something until I discuss it with myself. I think he said in 5 different languages or something like that, or at least in several different languages. So similarly, doing it different ways can help us understand it. Finally, the last way to both either solve or to think about a problem is verbally, right? To try to put it in the English language and discuss it that way. So those are 4 different ways of getting and thinking about a solution. So we'll hit all of those in this chapter. So anyway, how do we do this one analytically? And before I can give you the answer, I have to first teach you something from Calculus 2, which if you haven't had Calculus 2, you don't know yet. Remember in Calculus 2, I mentioned that you spend quite a bit of time learning how to find antiderivatives. And here is one of the most important way of finding antiderivatives which is going to be useful here. It's called integration by parts. And if you're following along with the textbook, this is all in the textbook, but I'll go through the details here. Integration by parts. And the way I'll teach that, I'll do it the same way as I did in the textbook. I'll say, okay, suppose we have two functions, and quite often authors will use u and v for those two functions. So you take two functions, you multiply them together, and then you take the derivative. And you know, hopefully, that when you take the derivative of the product of two functions, you have to use a product rule. You take the derivative of the first, which I will write as u prime of x, and then you leave the second one alone, times v of x, plus I leave the first one alone, u of x, times the derivative of the second one, v prime of x. Okay, there's your product rule. So once you have that, then you can manipulate it a little bit. So let's leave this on one side and let's bring this over to the other side. In fact, I'm going to make this one positive. I'm going to write that as u of x, v prime of x is equal to, if I bring this over, it's going to be u of x, v of x, whole thing prime minus, I'm going to write it as v of x times u prime of x. Everyone agreed we can do that? So this is on one side, you bring this over to the other side, flip those two around, you got that. So this is equal to this, and so now we're going to say, okay, if this function is equal to this function, then the antiderivatives are equal. So now I can take the antiderivative of this side, and I'm going to write it as just like this, u of x, v prime of x dx is equal to the antiderivative here. And here I'm going to break this up and take the antiderivative of each one, which of course we can. I'm going to write it as u of x, v of x, product prime, dx, minus the antiderivative of v of x, u prime of x, dx. Okay, are you all with me? And so now let's evaluate this. I could leave it like this. I'm just going to just to get rid of all those x's. I'm just going to rewrite it like this now. I'm just going to write it as u, and then this thing right here, I could is recall that is dv. Agreed? Because when we've been using substitution and so on, dv is what you get when you take the derivative of v and slap on the dx, right? That's the differential. So this thing right there is dv. And now what about this side? Notice here I'm taking the antiderivative of the derivative of a function, and when you do that they undo each other and you just end up with a function back. So I could write that as u of x times v of x. So I'm just going to write it as uv, and then minus here, again, I could put all those x's in there, but I'm just going to write it as v, and then all of this is, I'll write it as du. And that right there is the formula for integration by parts. And so let's see once. I'll write it up here because that's what we're going to be using today quite a bit. It's all up there, just barely. Let me make sure it's there. There we go. Okay, there it is. Okay, so there's the formula. So how can we use that? What's that useful for? So we're doing all this before we get back to this again. There's the formula right there. And so let's see once how we can use it. So where this is useful is when you have functions that involve two different kinds of functions. So here's an antiderivative, and we have two different things here. We have an exponential and we have an x there. And I want to find the antiderivative of this thing. Okay? And the question is, how do we find the antiderivative of it? And so let me show you how you do it using this formula. We choose part of this thing as our u, and we choose part of it as the dx. So I'm going to choose this for the u, and I'm going to choose all of this for the dx. And so I'm going to go down here below here, and I'm going to write u is equal to x. And then I'm going to do the opposite corner here. This is dv. dv. This is your u, and this is your dv. So there's your u. Here's the dv right there is equal to e to the x dx. Okay? Now, if this is u, then what's du going to be? Du is the derivative of this. The derivative of x is just 1. And then you always have to slap on your dx when you take the differential. It's the derivative times the dx. So you have that. And now we have to go backwards. What's the function v whose derivative is e to the x? So whose differential is e to the x dx? Well, you should know that. The derivative of e to the x is e to the x, and so the antiderivative of e to the x is e to the x. So there you have it right there. So here's your u, there's your v, here's your du, and here's your dv. And so now we use this formula, and what does the formula say? It says I take u times v, which is this times this, minus the integral of v du. So here's v, and here's du, and so we're going to get e to the x times 1 dx. E to the x times 1 dx. And now you see the value of this method, because I had something here where I had to find the antiderivative. I have something here where I have to find the antiderivative, but this one I can find. That one I can find, right? So let's go one step further and just write is equal to what? X, e to the x minus the antiderivative of e to the x is just e to the x. And so you have that. Of course, you always have to throw in your plus c. So there's the answer. Okay? So there's the antiderivative of this function. And if ever you are unsure of yourself or want to check, how do you determine how do you check that this in fact is the antiderivative of this? Right? You just take the derivative of this and you should end up with that again. Let's go ahead and do it just to check. If I take the derivative of this, I'm going to just off to the side here, if I take the derivative of this, I'm going to get, well here, let me write it all down. The derivative of x e to the x minus e to the x plus c is equal to what? I have to use a product rule here. The product rule says I take the derivative of the first times the second plus the first times the derivative of the second. And now I subtract the derivative of this, which is e to the x, and the derivative of c, of course, is just constant. And so these two things go away, and sure enough, the derivative of this thing is just what we started with. Okay? So that's called integration by parts. Now, a couple questions should come to your mind. One question is, how did I know to choose this as my u rather than to choose e to the x as my u? Why couldn't I have chosen this right here as my u, and then these two things together become the dv. The dv. And the answer is, that's fine. Go ahead and give it a try. Let's see once what happens if we were to do that. So let's get rid of this, and this, and this, and this, and let's see once what happens. So now I'm letting u be equal to e to the x, and dv is x dx. That's all good. Okay? So now du is what? The derivative of e to the x is, you take the derivative, it's going to be e to the x dx. And the antiderivative of v, what's the antiderivative? The antiderivative of x is just going to be 1/2 x squared. Agreed? There it is right there. And so what does the integration by parts tell us that this is equal to? It's equal to u times v So u times v is going to be 1/2. I'm going to write it as x squared e to the x. I like to put the x squared in front of the e to the x, minus the integral of v du. So there's v. Here's your du. I can bring the 1/2 out front again. I'm going to get an x squared right there. And then I'm going to get du, which is e to the x dx. Okay? So the good news is, this is perfectly good. This is true. This is equal to this. The bad news is, if we were in a hole here, we're in even a deeper hole here. Notice that here we had a 1x to the first power, now we've got an x to the second power. So if this was impossible to integrate, this is even harder to integrate, right? We can't, how do I find the antiderivative of that? So the point is, we could have done it either way, but one way led us to something which solved the problem for us. The other way is correct, it's just not helpful. Okay? So that's the point. Okay? So that's the first thing I want to say, is that you could do it either way, but one way is going to be helpful, the other way is not. So then the question is, how do you know which way is helpful? Well, one of the nice things about integration, rather than differentiation, is you don't always know. Sometimes you just have to give it a try and see once what works. Okay, so that's all fine. It doesn't hurt just to give it a try and see if it helps. If not, you try something else. But when I took a graduate topology class at Iowa State, my topology teacher in this class knew I was teaching this course, and he gave me a trick. He was Korean, so he actually spoke rather broken English, but he told me, he said, the word is late. That's the way to do it. And I said, what are you talking about? He goes, well, he said, this is the way to determine what your u should be. So I'm going to put a u right here, and whatever kind of function you first hit when you work down the word late, that is what you let your u be equal to. So what do these stand for? This stands for logarithmic function. Okay, it froze on me, but I caught it right away. So the first one is logarithmic. The second one is algebraic, which is powers of x, basically. Things like x, x squared, even a 1, things like that are algebraic. Can you guess what the other two are? Next one is trigonometric, sines and cosines, things like that. And what's the last one? Exponential. Okay, so basically, just like we did here, what did we do? We went down this thing and we said, I've got an algebraic and I've got an exponential. If you go from top to bottom, you hit algebraic before you hit exponential, so you let your u be equal to the algebraic one. And then you let your in this case, the dv be the exponential one. Okay, so that's just a little mnemonic device that I've never seen it not work, so it's really helpful. The other way to understand, just to get a pretty good idea of what you should let u to be, is just to think about what we've already done here. Basically, when you start with u and you end up with a du, see here you have a du, you basically want this function to become easier. This was an x and this turned into a 1, right? So it became a simpler function. And so that's kind of what you're after. When we started here with an e to the x and we end up with an e to the x there, that was no simpler, it was no harder, it was the same. But on the other hand, then our dv became x dx, and so when we had to find the v was the antiderivative of this, which was 1/2 x squared. See that? So this got harder. See this? Here's your v right there. So you want this thing, by the time you're done, to be a simpler expression than the one you started with. And so typically that's what you need to do. Okay? So that's the idea. So in Calc 2 is where you spend a lot of time with this sort of thing, but this is actually the guts of it right here. Okay? And in fact, let's do a couple more problems just to give you a little more practice with it, and then we will see how it all works. Here's one other one. Let's do this one. Okay, and I should have kept the word late. I'll just write it up here. Okay, so notice we have an algebraic and we have a trigonometric. See that? And so we're going to let the u be equal to the algebraic x. Du is going to be 1 dx. Then the rest of it is going to be the dv is going to be cosine of x dx. And then v is equal to the antiderivative of that, which is the sine of x. Agreed? And so this thing is equal to, what does it say? U times v, x times sine of x, minus the integral of v du. So it's going to be sine of x dx. See that? And so now you can finish it off. This is going to be x sine of x minus, what's the antiderivative of sine? The antiderivative of sine is the negative cosine of x. So there you go. Okay, and again, you can check that out, take the derivative, and you should end up with that one again. Okay, let's do two more. I'll do one that's not in the book. Let's do this one. X squared times e to the x dx. Okay, here again, we'll let u be equal to the what do you call it? The algebraic, and then dv is the exponential. And so now du is going to be 2x dx. Agreed? The derivative of that. And v is going to be the antiderivative of this, which is e to the x. So what happens when we use integration by parts? It's going to be uv x squared e to the x minus the integral of v du. Here's v, there's du. The 2 I can bring out front, and I'm going to get x e to the x dx right there. So you look at that and you say, wait a second, this is all good, but how do I find the antiderivative of that? And hopefully you don't have to think too hard, because you think, oh, wait a second, we just did that one a minute ago. We proved that the antiderivative of this was, I already forgot what it was. What was it? X e to the x minus e to the x, I believe, plus c. So then this becomes a bookkeeping problem. You have to be very careful. Let me block this off here. So I'm going to write minus x squared e to the x. Now be very careful. Put negative 2. That's there. Now I'm going to, for all of this right there, I'm going to put this stuff in. X e to the x minus e to the x plus c. And then you can go ahead and distribute this through this 2 through, and 2 times c is still just a c, so you could just write it as oh, here, let me finish it. So it's going to be x squared e to the x minus 2x e to the x minus a negative is going to be plus 2 e to the x, and then I'll just say plus c again. I'll call that c1 and just call that c. So there's the antiderivative of this, and again you can check it off by using the product rule or taking the derivative of this thing. You should end up with that by the time you're done. Okay, so you're getting a good what's the word? Overview, I guess, of integration by parts. Let's just do one more. This is one of my favorite ones. Okay, so you look at that and you say, well, there's no product there. I need the product of two things. And so you might look at that for a bit before it suddenly occurs to you, oh, let's just think of putting a 1 right there. Now by putting a 1 right there, I'm going to now, look at here. Now I let u be equal to the logarithmic. So it's going to be the ln of x, and dv is going to be the rest of it, 1 dx. And you say, why? Why will that work? Because now my v is going to be x dx that got tougher, right? To go from one antiderivative as x, that kind of seems to be going the wrong direction. But really, you had no choice, because if you would have let your dv be equal to the ln of x dx, well, heck, how do you find the antiderivative? That's exactly what we're trying to find. So that's why the logarithm has to be the first one in here, because if you're going this way, you don't even know what the antiderivative of the ln is. So now let's go ahead and let du, what's the derivative of this? Obviously that's just 1 over x dx. And so now, what do? We use the integration by parts. uv is going to be x ln of x minus the integral of v. Oops, I didn't want a dx right there. Okay, v du. And can I do that all in one step? X divided by x is just going to be 1, so it's just going to be 1 dx. See that? And so this whole thing then becomes x ln of x. This is a 1. The antiderivative of 1 is just x plus c. So there you go. Okay? So that's a quick review of integration by parts, which really, that together with, I guess I'll leave that up here, are really the two things from Calc 2 that you need in this course that you might not have known. The only other thing is going to be one very small thing from Calc 3. And that's basically it. Other than that, this course is really kind of independent of Calc 2 and Calc 3. Okay, so now let's get back to this again. So I'm going to write it as just y prime is equal to x plus y. That was our differential equation that we wanted to solve. So how do we solve that? Well, here's how we solve it. Okay? I'm going to give you a formula, which I typically don't do in this course, but this is a case where just learning the formula is the best way to learn how to do the problems. Suppose we have a function that looks like this. Notice that right there is a kind of a standard first order linear differential equation. You can do whatever you want with the x's, but the y and the y prime have to be just kept ordinary. You don't do anything to them at all. Okay, so there's a first order linear differential equation. It's first order, of course, because the highest derivative is the first. And by the way, if I had something in front of here, some function of x there, I could just divide the whole thing through, and then I'd end up with a 1 there, and I'd just change what my p and my q were. So you can always get something, a first order linear into this form. Okay, so how do we go about solving that? And it turns out that the way we get the solution to this is very similar to how we found the formula for integration by parts. We do something kind of similar. Here's what we do. It's a very clever idea. What we do is we multiply both sides by e to the antiderivative of p of x. Okay, if you have two things that are equal, you can multiply them by the same thing and they'll still be equal. Okay, now, whenever you do something in mathematics, students sometimes ask why. And there's two different ways in which they could be asking why. One reason would be is justify that. Why are you allowed to do that? And here the answer is simple. If you have two things that are equal, you're allowed to multiply equal things by equal things, and it's still going to be equal. So the justification is simple. The second way in which they ask why is, why would you want to do that? Why would you ever think of doing that? What's your motivation for doing that? And that's a good question here. Why would you want to? It looks like we just made it more difficult. And so you just have to trust me. You watch for 1 or 2 more steps and you'll see why we did it. Okay? So the first thing I'm going to do is to multiply this through. So I'm going to write it as y prime times e to the, like that, plus, I'll write it as p of x. I'm trying to remember exactly the best way to write it here, but I'll write it like this and hope for the best. Okay, so I can do that. And now, can you see what's special about this side? Can you see what's special about that side? Notice, if you want to, stop the video and think for a moment. See if you can see what's special about it. This thing right here is just the derivative of y times e This is just the derivative of this. Let's check it out. We have to use a product rule here. What does a product rule say? If you have the derivative of the product of 2 functions, what is it? You take the derivative of the first, there it is, the derivative of the first, times the second, you leave it alone, plus the first, oh, I have it in the wrong order, but that's okay. There's the first right there, times the derivative of the second. And what's the derivative of e to anything? The derivative of e to anything is, using the chain rule, e to that thing times the derivative of this thing. And what is the derivative of the top? The derivative of the top, well, if you take the derivative of the antiderivative of something, you just end up with that thing. See that? So the derivative of this top is just going to be p of x, right there. See that? So let me say it one more time. If I take the derivative of this thing, it's the derivative of the first times the second plus the first times the derivative of the second. What's the derivative of the second? It's just e to that thing times the derivative of the top, which is that thing right there. Okay, so that's the key. That's why we did all this. And so now I can just take the antiderivative of both sides here. Take the antiderivative of both sides, and when I do that, notice, same as what we did here, when you take the antiderivative of the derivative of something, you just end up with that thing. So it's just going to be y e and now you're going to have this whole thing over here. I'm gonna put it over here just so I can do one more step, and I'm going to write it as e to the integral of p of x dx times q of x dx. So this is all equal to this, and then finally we can solve it for y by dividing both sides by this, or by multiplying both sides by e to the negative of that, right? If I take e to the negative of that thing on both sides, then it will go away over here, and I'll get it over here, and there is your solution. Right there is your solution. So I'm just going to put the solution right up here. The solution of this first order linear differential equation is y is equal to e to the negative integral of p of x dx times the integral of e to the positive p of x dx all times q of x dx. Looks pretty impressive, doesn't it? There's your final answer right there. There's your final answer. So let's see once how that works. Okay, let's see how it works. So this is all by way of introduction. I tell you what, first thing let's do is just to do that one right there. So the first thing I have to do is to get it in this form. So I'm going to write it as y prime minus y is equal to x. Agreed? That's in the correct form. I want to get the y over to this side along with the derivative. So y prime minus y is equal to x. So now I know that my p of x is a -1, and I know that my q of x is equal to x. See that? So what does this formula say? So this formula says that y, the solution to that, is equal to what? E to the negative integral of, what did I say p was? I can go ahead and write it over here if I want to. P is equal to -1, q is equal to x. So I'm going to get a p of x is equal to a -1 dx. And then e to the integral, p of x again is just a -1 dx. And then q of x is x again. See that? Well, can we go from there? A negative of a negative is just positive. And so this is the antiderivative of 1. The antiderivative of 1 is just x. So this is just going to become e to the x right there. That's e to the x. What do we have here? The antiderivative of -1 is just going to be -x. So this is just going to be e to the -x right there. And then I still have my x dx right there. Okay, let me make sure that I'm still being taped. Oops. There we go. Okay, still good. Okay, now one thing that you might wonder about is, what about our constant of integration? Whatever the constant of integration is here, it also ended up being here, but one of them would be positive and one would be negative. So by the time you have a e to the c and an e to the -c, that all ends up just being 1. So the point is, there's no need to, when you find the antiderivatives of these things, there's no reason to even include the constant of integration, because they're both going to just divide out anyway. Okay? So no worries about that. So just leave that alone. But now let's go ahead and how do we solve this? So look at this and you say, how do I solve that thing? And hopefully, after just learned about it, you say, oh, this is where we can use integration by parts. So let's let u be equal to x, and let's let dv be equal to the rest of it, which is e to the -x dx. Okay. Then du is going to be 1 dx. That's the derivative of this thing. And v is the antiderivative of this thing. And I guess, you know what? This is something you should just know, is that the antiderivative of e to the kx is just 1 over k e to the kx. Do you agree? Plus c, of course. Because if you take the derivative of this thing, the derivative of e to the kx is going to be e to the kx times k, and that k comes and cancels with this thing, and you just end up with e to the kx. You could let u be equal to kx and do it by substitution if you wanted to do it that way, but it's easy enough just to see it. So the point is, here I just go 1 over -1 is going to be just a -1 e to the -x. There's the antiderivative. It's It's going to be negative 1 e to the negative x. So you've got that right there. And so let's finish it off. It's going to be e to the x. Okay, now you got to be careful here. What does integration by parts say? It says u times v. So notice it's this times this. I'm going to have a negative x times e to the negative x minus, be careful, minus the integral of v du. Here's my v, here's my du. Notice my v has another negative in it, so I'm just going to cancel that negative right there. And then I'm going to get my e to the negative x times du is dx right there. See that? That's all being multiplied by this. We have 1 or 2 steps left. It's going to be e to the x, negative x, e to the negative x. What's the antiderivative of this? Well, we just did it a minute ago. It's going to be negative e to the negative x plus c. Here we do need the c because here we're finding the antiderivative of this thing here, which in general is going to have a constant on it. And now, see this? All of that is being multiplied by this. And so when I multiply that all through, look at what happens. I'm going to get this times this is going to be a negative x. This times this is going to be a negative 1. See that? This times this, those things cancel. I'm just going to get a negative 1. And then this times this is going to be plus c times e to the x. So there is the solution. I think I would probably write it like this. C e to the x minus 1. And so there's the solution to this differential equation right there. Okay, so you got to be really careful that you don't just at the very end say, oh, I forgot a c, I need to throw a c on here. No, no, no. At the point where you take the antiderivative there, that's where you need the c, and then in this case you have to multiply that through by the e to the x, and it ends up being right there. Okay, so there it is. So let's go ahead and write this down. The solution is y is equal to c e to the x minus 1. Okay, and I want to do one more thing with this problem. Quite often when you have problems like this, these are initial value problems. Remember what an initial value problem is? It says we've got a differential equation like this, and we're told that, say, y of 0 is equal to 5, for example. We're told there's your initial value, just like we did with those temperature problems, right? Newton's law of cooling. So I say, oh, okay, if y of 0 is equal to 5, then we got to figure out what c is. So what do? So now it's an initial value problem. And so find c. How do we find c? Well, I know that y of 0 is equal to 5. And if I stick a 0 in here, I'm going to get a c minus e to the 0, of course, is 1. So it's just going to be c minus 0 minus 1. So solve that for c, and you're going to get what? C is equal to, bring the 1 over, c is equal to 6. So here is your solution. To this initial value problem. So there's a solution that both satisfies this differential equation and satisfies this. And again, how do you, if you wanted to prove to yourself, check that you actually had the right answer, all you have to do is do what it says. What does this differential equation say? It says if I take the derivative of y, let's go ahead and do it. If I take the derivative of y, what's the derivative of this thing? It's going to be 6 e to the x. The derivative of this is going to be minus 1. You agree? That's what that is. And it says that that better be equal to, if I take y, well, here's my y right here. And what do I do to y? I add x to it. If I add x to it, what do I end up with? This cancels this. I get 6 e to the x minus 1. Sure enough, I get that on both sides. See that? So x plus y is equal to that, which is equal to that. So sure enough, y prime is equal to x plus y. And also, sure enough, if I stick a 0 in here, what happens? I'm going to get 6 minus 0 minus 1 is 5. So it's an initial value problem. Okay, very good. So that's the idea. Now, the only other thing is to do a couple more examples that I've got in the text. And I don't know, should I do both of those? I think, there's a couple exercises and a couple examples. Let me just get you started. The main thing to notice about those all of them, is that they're all going to require integration by parts. Okay, let's get started on one. So I've got this one right here. This is example 315. Y prime is equal to x y plus x. Y prime is equal to x y plus x. And we're told this is an initial value problem. Y of 0 is equal to 5. Okay, so let's go ahead and see if we can do it. So first of all, I need to get it into this form. See that? So I'm going to go y prime minus xy is equal to x. Okay, so now I see that p of x is equal to negative x and q of x is equal to x. Okay, so what does the formula say? So our formula says y is equal to e to the negative integral of p of x. P of x is a negative, so the negative cancels here, and I'm just going to get an x dx, like that. And then here I have this integral. I'm going to get e to the integral of p, which is negative x dx. And then q is another x dx. Holy smokes, look at all those x dx's we have. Okay, well, let's go ahead. Where do we go from there? Y is equal to, what's the antiderivative of x? Just agree it's going to be 1/2 x squared. There's the antiderivative. What about here? The antiderivative of that is going to be e to the negative 1/2 x squared. Agreed? And then we have x dx right there. We just make sure I've got the same thing I do in the book. It's looking right. Okay, yeah, that looks right. So now, where do we go from here? How do we finish this off? Is this something where we need to use integration by parts? We've got an algebraic and an exponential, so we probably could, but the first thing you should always look for is a substitution. If you can get an easy substitution, that's by far the best way to do it. And notice, right here, if I just let u be equal to negative 1/2 x squared, then du is going to be equal to, what's the derivative? It's just going to be negative x dx. See that? So right here, I'm just going to get e 1/2 x squared. Okay, now, what's this going to become? This is going to become e to the u, and then x dx. X dx is going to be a negative du. So I can bring the negative out front, bring that out front, and there I have a du right there. Right? That's just your antiderivative. And now it's going to be negative e to the 1/2 x squared. What's the antiderivative of e to the u? Do you agree it's just going to be e to the u? So the antiderivative of this thing is just e to the u, and e to the u is just this right here. So it's just going to be e to the negative 1/2 x squared, right there. Plus c, obviously. Plus c. Notice how important that c is. Okay, because now when you multiply back through, notice what you're going to get. This cancels with this. Here you have a negative, there you have a positive. So those two things, when you add the exponents, they cancel. It's just going to be -1 plus c times e. Actually, minus c times e to the 1/2 x squared, like that. So, so you could leave it like that. I think it's easier to call this a C1. Think of that as a C1, and then negative C1 is just C, and then just make that a positive C again. So there's no reason to have more negatives in your life than you need. So negative times C1 is just C, and let that be your C right there. So there it is, and I'll let you finish it off. There's the answer, and now if you want y of 0 to be equal to 5, then figure out what c has to be. Okay? So there's that one. Let's get started on the last one that's also an example. It's this one right here. This is a lot of good stuff you're learning in this section. What is it? It is xy prime oh, I lost it. Let's see, where is it? Plus 2y is equal to sine of x. Okay, I guess this is an important one to do, because notice this is not of this form, right? I want something that looks like this. And so the very first thing I can do is to rewrite it like this. Y prime plus 2 over x times y is equal to sine of x over x. Agreed? So now I've got it in this form right there. And yep, it's all set. So my p of x is equal to 2 over x. My q of x is equal to sine of x over x. Agreed? So what does our formula say? Y is equal to e to the negative integral of p. And the integral of p is going to be 2 over x dx. And then what? Times the integral of e to the p of x, which is integral of 2 over x dx. And then q of x is sine of x over x dx. This one has me scared, to be honest with you. I'm not sure I see the answer to this one. Hopefully it works out. Let's see what happens, okay? Here we go. Oh, maybe I see it. Okay, so let's do a couple steps in one here. First of all, let's think about this. Let's just do a little stuff off to the side here. So if I had a lot of board space, I'd do it all off. But let's do a little work here. Let's do this one right here. 2 over x dx, that's just 2 times 1 over x dx. And the antiderivative of that is just the ln of x. Agreed? It's just the ln of x. Okay. I tell you what, we would have trouble if x was 0 here. So at the very start, let's, for this one, assume that x is greater than 0. Then I won't have to worry about taking the absolute value. In fact, do I do that in the book? Yes, I do, in fact. Yep, x is greater than 0. So we're going to assume x is greater than 0, so that makes this simple as well. Okay, so we've got this. Okay, so this is the case. This is equal to this. So when I take e to this thing right here, notice what we have. E to the 2 ln of x is just equal to, there's a couple ways to do it. I could write it as e to the ln of I could bring this 2 up here and write it as ln of x squared. That's a property of the ln, and now these two things undo each other, and you just end up with x squared there. E to the ln of anything is just itself. That's one way of doing it. Another way of doing it is to say, oh, that's equal to e to the ln of x quantity squared. I could write that like this. And then again, this is going to be x squared. So either way, this becomes an x squared right there. And this is going to become, let's see, this is x squared, and this is going to become x to the negative 2 power. I'll let you figure that out for yourself the same way. So this thing right here is going to be x to the negative 2 power, which is 1 over x squared. By the time you're done evaluating this, because it has a negative, it's x squared, but it's all of that to the negative 1 power, which is 1 over x squared. Okay? So, yep, okay. And then this is going to be what? It's going to be x squared, and then I have an x, or a 1 over x there rather, and then a sine of x. See that? You got all that? And now, this is going to be 1 over x squared. This all reduces just to x, sine of x dx. Okay, so you have that. And now, do you see how you finally finish this thing? Here's the product of two functions right there. So I can let u be equal to x, du is equal to dx. Here's my dv. dv is equal to sine of x dx. Be careful. So what's v? v is the thing whose derivative is this. v is the negative cosine of x. So this is all equal to 1 over x squared times, what does integration by parts say? uv, so it's going to be a minus x cosine of x, uv, minus the integral of v du. Here's my v. Notice v has another negative in it, so I'll leave it right there. Cosine of x. du is just dx. Ah, that's kind of nice. Okay, so we're making headway here. So we're going to get 1 over x squared times negative x cosine of x. The antiderivative of cosine, of course, is just sine of x. Here's where you need your c. Make sure you have your c there. And so by the time you're done, it's going to be what? It's going to be a negative cosine of x, all divided by, this is x over x squared, is all divided by x, plus sine of x divided by x squared, plus c divided by x squared. This is that's just not a constant there. That's your variable. So that c stays there, and there it is right there. Let me make sure you're still with me here. Dang it. There you go. Very good. Okay, so there it is right there. So there's the answer. And again, just if you wanted to check, you could do exactly what it says. Take the this is your y. This is your final answer. So if this is equal to y, what does this say to do? You first take the derivative of that, and then you multiply it by x, and then you add 2 times this thing. And by the time you do all that, you better end up with just the sine of x after everything cancels. Okay? So that's I think a very thorough explanation and introduction, well, more than introduction, total explanation for using solving first order linear differential equations. Okay, so you've got a couple other examples to do, and in the next video we're going to now apply this to a bunch of real world problems again. Okay, usually in this course I like to first give the problem and then the application. In this particular case, I'm giving you the formula first, the solution first, and then we'll see the application in the next video. Very good.